Am I bouncing? La la la. Okay, I will begin. Loving Father, we thank you for this day. I thank you for these students. Just ask you to bless our work today, Lord. In your name I pray. Amen. So today, what lecture are we on? I lost track. What lecture? Do you guys remember? 18? All right. Lecture 18, which is on matrix groups. And so what I wanted to do was just to take some time in here, just focus our attention on matrix groups and perhaps some interesting theorems which are known for matrix groups. And so what is a matrix group, right? So we can, of course, talk about real matrix group. What's a real matrix group? It's some G which is a subgroup of GL n comma R, right? So it's some subgroup of n by n matrices which is invertible, right? Now typically, I mean, we could look at G equals to GLN, right? But there's all kinds of special subcases which are interesting, right? So this kind of matrix, kind of group is a matrix group. It's a group of matrices. I mean, not, okay, great. You could also talk about a complex matrix group, right? You could look at a subgroup. What would a complex matrix group look like? It'd be something like, say, G would be a subgroup of GL, let's say, M, C. So sufficiently, some M by M invertible complex matrices. You could look at matrix subgroups of that. All right, those would also be matrix groups. You could also talk about quaternionic matrix groups. Quaternionic matrix groups. That would be G, a subgroup of G, L, I don't know, K, H. All right. In fact, this also is a well-defined construction. You can look at the set of invertible matrices with entries that are quaternions. What is a quaternion? So we've got R, right? And then that's a subspace of the complex numbers. And you can view the complex numbers as a subspace of the quaternions if you like, right? So if you think of these as vector spaces, what do we build the real numbers with in terms of a real span? This is kind of silly, but 1, right? The basis for real numbers is just 1. And then how do you get complex numbers? Right, over here you've got something like, so, basically we've got A. Over here we've got A plus IB, yeah? Something like Z equals to A plus IB, typical complex number. Now a quaternion, I'll say Q. Q is something like, let's say, T plus Xi plus Yj plus Zk. Now we've looked at Q8, the quaternion 8 group. That's a particular finite subgroup of the quaternions, all right? It's built with these versors, the I, the J, the K, they're negatives, as well as plus or minus 1. There's 8 things, right? It's non-commutative. We've had a problem on this, I believe. But this is the set of quaternions here, T, X, Y, and Z. These are all real numbers. So if you identify T, number 1, I, J, and K with the unit vectors E1, E2, E3, and E4 a la linear algebra, then as a point set, we could think of the quaternions as just being R4. So it's really an element of R4. So the quaternions are essentially R4 with a kind of funny multiplication. Are any of these groups? Oh, yes, they are. I wanted the answer to be no, but the answer is yes. What kind of groups are they? Additive groups. Very good. Are these any of these multiplicative groups? The answer is no. Zero's in there, right? Zero does not have a multiplicative inverse. However, these particular objects, the real numbers, the complex numbers, and the quaternions, are examples of skew fields, or in the case of the reals and the complexes, just fields. What that means is that every non-zero element has an inverse, a multiplicative inverse. Now, the quaternions would be a field, except that they're not commutative, right? A field is a commutative ring with identity in which every non-zero thing has a multiplicative inverse. We'll soon be talking about rings more properly. It won't be long. But I wanted to point out that this quaternions, we could also look at this as, check this out. So this could also be written as, let's say, curses, how to say this, t plus xi plus, let's see here, how can I, trying to think, we've got ij equals to k. There's a way to write this as a complex number, something of the form, let's say y plus I z times something. What's that? J, is that legit? I think you're right, because I times j is k, which is what we have in the line above. And so you see that a quaternion could also be understood as the sum of, say, z1 plus z2 times j, where z1 and z2 are what? Elements of the complex numbers. If we understand things of the form a plus bi as being complex numbers in the quaternions. So what I'm trying to say is there's a natural identification of the complex numbers sitting inside the quaternions, right? And in fact, we can look at any quaternion as a pair of complex numbers. Okay? And of course, the real numbers also are sitting inside the complex numbers. In fact, if you look at the quaternions, the numbers in the quaternions which commute with all other numbers are just the real numbers, it turns out. All right, so the center of the quaternions is just the reals. What's the center of the complex numbers? What complex numbers commute with all other complex numbers? Admittedly, I'm generalizing the notion of center a little bit here, right? Because we talked about center for groups. I'm talking about commuting in the multiplicative sense, and admittedly, complex numbers are not a group, so this is an abusive terminology for you guys. You'll forgive me? I just pushed your test back. You'll forgive me. Right? Yes, okay. But my larger point here is a simple one, which is that there's a natural identification of, there's an interplay that you can make between reals and complexes and quaternions. You might ask, does this story go on? Are there other division are there other what are called associative division algebras? An associative division algebra, what is that? It's a set which is a vector space, all right? So you have a way of adding things, and you also have a way of multiplying things in an associative fashion. An associative, and what's division? Division algebra means that every non-zero thing has an inverse. All right. So these are examples of associative division algebras. And Frobenius proved in 1877, up to some notion of equivalence, that these are the only division algebras of, well, characteristic zero, I suppose. There's another story that could be told, I suppose, over finite fields. I'm less educated about that, so let me not try to say much about that here on the fly. So one of the interesting things about matrix groups is that if you have a complex matrix group, or if you have a quaternionic matrix group, there's actually a standard technique to rewrite them as an isomorphic real matrix group. You can take a complex or a quaternionic matrix group and you can repackage it as a real matrix group. That's one thing that's very, very interesting. And you've already started to see some of that in your linear algebra course. Here's a simple example of that thing that I was just saying. What if we have a 1 by 1 complex number, otherwise known as A plus IB? This is an element of the complex, complex. And we could think of that as being, let's say non-zero, so then that's GL, GL1C, I suppose. All right. To what natural 2 by 2 real matrix does this correspond? So this is actually interchangeable with the 2 by 2 real matrix AB minus BA. I mean, you could make that a map, give it a name, I don't know, rho, why not? So rho is a mapping from non-zero complexes to, in fact, GL to R. It's not surjective, right? But you can check that this mapping rho satisfies the following properties. Z times W is equal to rho Z, rho W, like that. And in fact, it also preserves addition. In fact, that's that's not a bijection. I should be careful. It is an injection, though. What that's doing is it's giving us a copy of the complex numbers inside 2 by 2 real matrices, right? And if we focus our attention on invertible complex numbers, it gives me invertible 2 by 2 real matrices of that form. So essentially what you can do, if you've got, you can just do this trick again. Suppose you had a 2 by 2 complex matrix like this. Suppose you had a complex matrix Z1, Z2, Z3, Z4, and you wanted to, so here's a 2 by 2 complex matrix. What would the corresponding real 4 by 4 matrix look like? What you do is just do this basically, row Z1, row Z2, row Z3, row Z4, like so. And so how big is the corresponding real matrix? So 2 by 2 complex matrix. So you could, maybe this is row 2, and the one I had up here was row 1. I don't know. So how big is the image in row 2 by 2? What's that? It's a blocks, right? A 2 by 2, a 2 by 2, a 2 by 2 by 2 by 2. That's a 4 by 4 real matrix. So you can build a 4 by 4 real matrix which corresponds to a 2 by 2 complex matrix. You can take a question in 2 by 2 complex matrices and convert it to a corresponding question in 4 by 4 real matrices if you like. I will spare you the details about the quaternions, but it is well known how this is done. So I think this is kind of neat that, so first of all, like the first simplification is if you're thinking about matrix groups built over real division algebras, which is just the reals, the complexes, or the quaternions, any matrix group can be viewed instead as a real matrix group. So studying real matrix groups is pretty general. So if you can develop a theory for real matrix groups, you've covered all the other cases implicitly because there's these correspondence. So that's kind of interesting. All right. So what are some examples of matrix groups? Number one, obviously, GL, GLNR is itself a matrix group, right? The set of invertible n by n matrices. But we've had other ones, right? We've talked about O and R. What was that? This is the orthogonal n by n real matrices. What did that look like? That was A in Rn by n, such that what? Such that A transpose A equals to the identity. This was the set of orthogonal matrices, right? I think we've proved this was a group, right? I think. You could prove it was a group, right? This would be a friendly final exam question, would it not? Subspace test, pretty straightforward. Not that bad. Let's see here. What else could we do? What's a subgroup of ONR? So if we look at this one, what's the significance of this matrix group would be one of my questions. Why do we care about the orthogonal group? What does it preserve? Central fact about the orthogonal group is that if we have A times X, right, and we take the dot product with A times Y, what's that give us? That gives us, AX transpose AY, which of course is X transpose AY, which is X transpose IY, which is, by the way, X dot Y. So the significance, one of the primary significances the significance, I would say, of the orthogonal group is it preserves dot products, right? It's also the case if you take the columns of an orthogonal matrix and you list them, it gets you an orthonormal basis. That's also an interesting aspect of an orthogonal matrix. So what about the determinants here? What's the determinant? We got what? Determinant of A, transpose determinant of A, which is what? Determinant of A squared equals to 1. So the determinant is what? Plus or minus 1, right? Aha! So this set of orthogonal matrices has two different kinds of determinants. It has either determinant 1 matrices or it has determinant minus 1 matrices, right? We have a name for the ones with determinant 1. What do we call those? Special orthogonal group here. So SONR is equal to, A and ON are such that the determinant of A is equal to 1. Generally speaking, the examples I'll show you, if we tack on an S, it makes the determinant 1. All right, so that's the special orthogonal group. Now, if we look at n equals to 3, we can think geometrically. The full orthogonal group includes isometries which turn objects inside out, right? Like they rip spheres inside out or cubes or whatever. These are determinant minus 1 transformations, reflections, perhaps. But on the other hand, determinant 1, those are the rotations in 3 dimensions, right? All right, so that's the orthogonal group. Do we have other examples? Well, I can give you kind of an uber example, if you will, which is, well, before I get to that though, we can also talk about U, the unitary group of order n. This is a subgroup of GL and C, right? What's the unitary group of order n? UN, what is this? This is A in Cn by n, such that I believe A dagger A is equal to the identity. Here, A dagger means A transpose conjugate. So it's the conjugate transpose, or the Hermitian adjoint, as it's sometimes called. Now, why define the unitary Why do you define unitary matrices like this? What is it that they're good for? Well, if we define the inner product on Cn, so the analog of the dot product for complex n space, right? How is this done? If I have x and y, it's defined to be x1, y1 bar plus x2, star. What do you guys want from me? Stars or bars? Bars? All right, fine. I've been doing bars. My upbringing includes both stars and bars. I like both. I don't know. It's hard for me. Okay, so maybe I should just invent yet another symbol for complex conjugation and use that, and insist that everyone else use it. Let's see here. Y2 bar. Bar. Yes, I decided on bar. Okay. So x1, y1 bar plus x2, y2 bar plus da 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 da. So it's almost like the dot product, right? Except what? Except that you got complex conjugates on the second thing, right? So the complex inner product, right, is not symmetric. It's conjugate symmetric. Now, and it's not bilinear either. It's linear in the first slot, but it's conjugate linear in the other slot. So let me just be clear on here. So like the properties of this inner product are a little bit weird. So if I have cx plus yz like that, it's cxz plus yz. Fine. That's just ordinary linearity in the first slot. But in the second slot, you have this kind of weird property that constants pull out with conjugates like that, right? And also, it's not symmetric, but we do have this. xy conjugate is yx. So I don't know if you had my linear algebra, you saw this, but if you didn't, I'm sure you didn't. So because other people are smarter than I am in terms of what they try to cover in classes, and much smarter. Anyway, this is the analog for a complex vector space, in particular Cn, of the dot product. And you can study orthogonal complements like perpendicular spaces and all that good stuff with respect to this complex inner product. So what's the significance of unitary matrix? If A is a unitary matrix, then we get the following fun fact. If we have AX, AY, well, this, by the way, can be rewritten. This formula here, we could rewrite that as X transpose Y conjugate. That's one way we could write it. And so I take AX, I transpose that. I take AY, I complex conjugate that. Complex conjugate is nice. It just, there's no sock shoes. You just do this, right? You just cut your shoes and socks in half or whatever. I don't know what that would be. Anyway, next step. This is X transpose A conjugate Y. What's that? It should be Y conjugate. Thank you. Thank you. Now, in my current approach, I have worked myself, like poor planning on my part, right? We had to do some work here. A conjugate transpose, right? A equals to I. What's this say? I need to figure out what A transpose A bar is, right? So if I take the complex conjugate of this whole thing, what do I get? I get A bar transpose bar A bar equals to I bar, right? Which tells me that A transpose A bar equals to I. Yay! So this is an alternative definition for a unitary matrix, which I'm not fond of, except for the purposes of this proof, because that is the identity. And so there you go. You got your X transpose Y bar, which of course is the inner product of X and Y in the complex sense. So unitary matrices are the analog of orthogonal matrices with respect to the complex inner product. Does that make sense? You're like, what's a complex inner product? Well, they're interesting and important to many applications that all of the concentrations in mathematics cover here. So, for example, Hilbert space is a complex inner product space which has this kind of structure. Anyway, you can also talk about SUN. What's SUN? I think you know what I'm going to say here. We're looking for A and UN such that what? The determinant of A equals to 1. There you go. These are the so-called special unitary matrices. It turns out these have profound significance in modern physics. For example, the standard model of particle physics is based on a fundamental symmetry group that's the direct product of SU2 and SU3. See, I think it's, oh, and I forget. Well, there's an SU2 for the electroweak symmetry, and there's an SU3 for the color, the quarks. Quarks have an SU3 because they come in 3. The electroweak has an SU2, and that breaks into like a U1 cross something. I forget exactly. It's where the radioactive decay comes from, and the U1 ends up being the symmetry group that's attached to the photon. So light, in fact, electromagnetism, you know, the physics that tells us how light propagates and everything, is in fact a gauge theory with gauge group U1. U1 being unitary matrices of order 1. We've already studied U1 in here. U1 is the what? What is U1? We're looking for a 1 by 1. What's this break down to when you take n equals to 1? What are you looking at? Let's say Z, right, in the complexes, right, a 1 by 1 complex number. I mean, a complex number. So let us agree that 1 by 1 we are going to identify with complexes. Like, no, you must put brackets around them. No. That's the kind of talk that will put your test back to where it was before. It's the only joke that's working today. But anyway, so stars and bars, bars and stars. I'm going to go with my underlined one. Z transpose, Z transpose, Z bar. What's the transpose of a number? Right. Well, I'll put the identity here, the 1 by 1 identity. So this, it just becomes Z bar equals to 1, also known as the modulus of Z squared equals to 1. If you break this into x plus iy, the condition that we have here is simply that x squared plus y squared equals to 1. So geometrically, U1 is just the unit circle in the complex plane. All right? And so that opens the door to my, now there are many other matrix groups. These are the most sort of common ones. I've shared with you some other ones. I'll briefly remind you the other one. I like sometimes to talk about G sub j, which is a subgroup of GL and R defined as follows. G sub j is A in Rn by n such that A transpose J, A equals to J again. So you can, and all you need is that this J is some invertible matrix. It oftentimes is chosen to be symmetric, but it could be different things. So let's see here. Let me just say a word or two. You guys tell me, though. I often assign this as a homework question. I don't think I hope this isn't a future homework question I'm working on. I feel like it is. So if I take J equals to the identity, what do I get? What's GJ? It's just O ONR, right? Because that's just orthogonal matrices. Now, interesting, other case, let's think about, we could think about n equals to 4 and eta equals to, say, minus 1, 1, 1, 1, right? Then this condition, this set of matrices are what are called Lorentz matrices. These are the allowed coordinate transformations in time space. Because, well, the minus come first, so it's time space. So this would be often denoted O13 would be by GJ in this case. These are Lorentz matrices. Or Lorentz matrices, which are the matrices of Lorentz transformations. They correspond to a combination of rotations and also velocity boosts in 4 dimensions. Yeah, that's what those are. Now, you could also play a different game here with this example. You could do something like eta equals to minus 1, da da da, minus 1, da da da, and then ones. And suppose you've got p of these and you got q. So suppose you got p minus 1s, you got q 1s. It's otherwise 0. This would define gj. And I'm saying that that's my j. Sorry. I meant to say that's the j. You guys should ask me about that, yeah? So here gj is known as O p comma q, I think, in my current notation. So I had p equals to 1 and q equals to 3 in my Lorentz matrix example. These would be the transformations corresponding to something that had, in some sense, like p time-like dimensions and q space-like dimensions. So there are people who study 2 or 3-dimensional time. I have no idea what that means, right? But would I rule it out? I would not. I mean, God said his ways are not our ways. Who am I to say that time is 1-dimensional? I think our ideas about how creation was created and how God understands the physics which he's using to control the universe, I think our ideas are all wrong, frankly. Like, radically wrong. We see shadows of the deeper reality. We do not see the reality for what it really is. That's my own personal opinion, but there you go. I'm not saying physics isn't useful. I'm just saying that physics is approximate, both in terms of concept and in law. But the conceptual approximation is what should be more frightening to you when you hear people give arguments which are based on the existence of things which don't exist in all likelihood. Ask yourself this question: how can you give arguments about non-existence based on physics which is incomplete? Here's a description of here's a description of 98% of a group. Here's an element. Prove it's not in the group. Could you do that? Obviously not, because you don't know the 2% that's missing. The 2% matters when you're talking about existence. Anyway, just a thought. I used to labor under the delusion that mathematics had to be physical, or that meant something. I no longer think that way. I think mathematics could be physical, but it doesn't have to be. Because I'm not sure that we really can know what is physical in the truest sense of the term. Excuse me. So this brings us to geometry. Oh, there's one other case over here I forgot. There's something even weirder. Something even weirder still. Weirder still. If we take j equals to 0, minus 1, 1, 0, like this, then look at the matrices which satisfy the condition A transpose J, A equals to A again. All right? Then those are called symplectic matrices. This gives us SP, and here's where I'll get into trouble. I'll say SP2, but I'm not really sure about that. It depends on which book you're looking at, all right? But let me see if I can find a nomenclature from a book at least. So the books which I'm not doing justice today to, Benjamin Steinberg's Representation Theory of Finite Groups. I've covered almost none of this. All right. Matrix Groups for Undergraduates by Christopher Tapp, a fantastic book. I've covered almost none of this. And last but not least, Matrix Groups, An Introduction to Lie group Theory by Andrew Baker. Again, I've covered almost none of this, and all of the mistakes and or misconceptions are due to me today. But he does have nomenclature here. He calls it simp2m. All right, I'm getting there. Simp2m is a subset of GL2m. Simp2m. His notation, simp2 equal to GJ, I think. Symplectic 2x2 matrices. If you wanted to look at, you could also look at symplectic 4x4. The symplectic matrices always come in even sizes. Odd, we don't talk about odd symplectic matrices. Even, so the next would be like a 4x4. And so the 4x4, you take J equal to 0, minus 1, 1, 0. 0, minus 1, 1, 0. Oh. This is why I brought this book. Yes. Okay. I was worried. And there's zeros over here. So this, it's the matrices like that transpose times J times that again gives you J again. This would be an A, if you had A transpose J A equal to J again. Let me call this J4 just so you can tell the difference. This would imply that A was an element of simp4. There you go. A 4x4 symplectic matrice. Now, these also preserve a form. You can actually construct an inner product on the quaternions, or vectors of quaternions. And the symplectic matrices correspond to preserving the inner product on quaternionic vectors. It would take me more time to really build that up carefully in here. There's a lot of conventions that I have to be careful about because quaternions are nefarious. All right. Okay, so there you go. That's a very healthy set of examples, I think. These are all matrix groups. Oh, one I forgot. What's the in category 1? What's the one shame on me? This one's important. One of you already mentioned it. What about SL and R? So that's just what? So that's the special linear group, right? All right. Let's just take a step back and think about all of these examples. Are any of them isomorphic to dn? What about Zn? How about a direct product of Zn and Dn? How about Sn? Symmetric group of order n. Or the alternating group. Are any of these going to be isomorphic to those? Why or not? Yeah? No. Why not?
They're all infinite.
They're all infinite is the correct answer, yes. These are all infinite groups. Their cardinality is the continuum. In contrast to most of what we've been doing, right? These are all infinite groups. Sometimes these are called continuous groups. And the reason that they were classically called continuous groups is because you can talk about continuity in them. You can talk about how close two matrices are to each other. You can talk about the concept of closeness for two matrices. You can talk about sets of matrices and whether those sets of matrices are open or closed. All right? All of your favorite ideas from calculus actually bear they work out in this context. You can define calculus over these kinds of matrices, all right? And that formal study of the geometry of matrix groups leads us to what's called a Lie group. What's a Lie group? I'll give you a informal definition, all right? A Lie group is an abstract group, like we've been studying this semester, on which you can do calculus. So, and to give a slightly more technical definition, it's a group where the group operations are smooth in the sense that the manifold structure of G demands. So in other words, a Lie group is both a manifold, which by the way is an abstract set on which you can do calculus, and an abstract group. It's both of these things at once. It's the marriage of group theory and analysis, right? That's what a Lie group is. Matrix groups are the most important and easy example of Lie groups. Probably easiest. So, you know, like what's the dimension of these different spaces, right? Like, I think you could tell me what's the dimension of U1, right? U1 is a matrix group. It's a manifold, right? Let's talk about manifolds in the heuristic sense we learn in Calculus 3, right? This is a space. What's its dimension? No, not 2. I mean, let me draw a picture. Not 2-dimensional now. No, still not 2. You guys cracking me up. So what do we mean by manifold dimension, or the dimension of a space in Calculus 3? If you zoom in on it, right, it looks like what? Like if you just zoom in on that part and just bring it over here and just, it's like, it's a line, right? There's a one-to-one correspondence locally between the unit circle and the real line. Just locally, not globally, of course, but I mean, this is a one-dimensional space. A curve is a one-dimensional space. Yeah? Let me ask a harder question. What's the dimension as a space of some of these other matrix groups? How big are they in terms of their dimension? How would you figure out what the dimension of, say, I don't know, let's pick out something relatively simple. How about GL2? I can't decide, guys. Is it GL2R or is it GL2R? Yeah? My apologies, but you know, my bad. So what's the dimension of this? So let's think about it, right? Think about it in terms of parameters. What is your condition? You've got A, B, C, D, such that what? AD minus BC is not equal to 0. What's the dimension of this space? In contrast, what if we talk about SL2? So there we've got A, B, C, D, such that what? AD minus BC equals to what? To 1. So it's a little bit tricky, all right? But the answer to the first question I asked you is actually 4. GL2 is 4-dimensional. Because we're just saying it's not equal. So that does not fix any of the variables. It just says as a whole they can't be 0, right? But that doesn't fix one in terms of the other. In contrast, AD minus BC equals to 1 allows me to solve for one of those 4 variables in terms of the other 3, at least in a place where the one that I'm solving for is not 0. For example, I can solve for C, or let's solve for A. I can solve for A is equal to 1 plus BC over D for what? For any A, B, C, D such that what? What condition do I need to solve for A?
D is non-zero.
Yeah, D is non-zero. So for this kind of matrices, I can tell you a chart, which is the reverse of a parameterization that you learned in Calculus 3. So like an unparameterization is what a chart is. But this chart would just be, it's kind of boring. It's, it's BCD. And the inverse to this chart, which would be a parameterization, would be what? That's the inverse to the chart. You can check that the determinant of that is 1. And at each point in SL2, you can find such a bijection between SL2 and R3. And this is why SL2 is a 3-dimensional manifold. So just to make a long story short, any of these examples which are defined in terms of an equation will end up being manifolds, where the dimension is determined by the number of independent equations in the defining condition. It's like what dimension would O3 be, for example? Well, it's simpler. How about SO2? What's that look like? SO2 is a 2x2 special orthogonal matrix, right? Which means it is a rotation. I think we've worked this out before. Anyway, you can show that this matrix looks like the following: cosine theta, sine theta, minus sine theta, cosine theta, something like that. So SO2, what's its dimension as a manifold? How many people here have not had Calculus 3? Did I see a hand? Okay, good. Makes me happy. I'm always afraid to ask that question in linear. All right, but the answer is what? I say 1? 1-dimensional? Okay. You are correct. How about SO3? What's SO3 look like? So there, the condition is A transpose A equals to I, right? And what else? The determinant of A is what? Is equal to 1. And so you got to sort through, like, how many conditions does that actually work out to? So I actually had you work this problem in linear algebra. You didn't realize it at the time. But I basically asked the question for you to show that any rotation can be written as a what? I think, you can find an axis for the rotation. And you find the axis and then you rotate, right? There exists a basis such that A can be written as a 2x2 rotation with a 1 down there. I'm not finding I think it's 3-dimensional. I could be wrong about that. I don't know. What's the dimension of that? I don't know. Right off the top of my head. But there are interesting questions that I'd like to explore further next class, which is, are any of these matrix groups isomorphic? What are their centers? Can we calculate the center of any of these matrix groups? What do they look like? Are these isomorphic? What else can we say about the manifold structure. Now, this is not a manifold theory course, right? So I'm just saying these words in a heuristic sense to you. I'm going to ask you 2 homework questions about it, right? So that your responsibility on the test will be largely focused by these 2 homework questions, right? And the easier things I say in here. So, you know, don't be terrified by me today, please. So anyway, I guess that's it for today. Thanks, guys.